In this example, we will find the least squares polynomial approximation of degree 10 for a given function over the closed interval from x equals 0 to x equals 3. F is the piecewise function where f of x is 1 minus x for x less than or equal to 1, x minus 1 if 1 is less than x less than or equal to 2, and 3 minus x if 2 is less than x. Let p of x be the least squares polynomial approximation where p of x is the sum of a sub I times x to the ith power, and I goes from 0 to 10. If p of x is the least squares polynomial approximation of f over the closed interval from 0 to 3, then p must minimize the least squares error e, which is given by the integral over the interval from 0 to 3 of the square of the difference between f and p. The exercise calls for finding the coefficients a sub I of the polynomial p of x. Since the a sub i's are the unknowns, and if the least squares error e is minimized, then the partial derivative of e with respect to a sub I should be 0 for I equals 0 to 10. One can show that if f is continuous, this equation is equivalent to the equation that the integral from 0 to 3 of the product of the difference between f of x and p of x and x to the ith power equals 0. For this exercise, we are going to use a software called Mathematica to solve for the a sub i's. We begin the Mathematica code with some preliminaries. First is f of x. We use an if-then-else statement to define f. We type if open square bracket x less than or equal to 1 for the first interval in the definition of f. If x satisfies this inequality, then f of x is equal to 1 minus x. Otherwise, or else, we have x greater than 1, which brings us to the other two pieces of f. We use another if-then-else statement so that we will have a nested if-then-else statement for the definition of f. The second piece of f is for x greater than 1 but x is less than or equal to 2. So the first entry in the inner if-then-else statement is x less than or equal to 2. Then it's x minus 1, which is f of x for x greater than 1 but x less than or equal to 2. The last entry within the inner if-then-else statement is 3 minus x, which is equal to f of x for x greater than 2. We just make sure now that all the brackets are paired up. Next, we write up the endpoints of the interval. We designate the left endpoint as x min. X min is 0. We designate the right endpoint as x max. X max is 3. Then we let the degree of the polynomial approximation be n. N is 10. Finally, we have our polynomial approximation. P of x is a sum of terms, and so we use the command sum with uppercase S. We are summing a sub I, which we write as a open bracket I closing square bracket, and to this we multiply x to the ith power. To complete the summation command, we indicate the range of the summation. I starts at 0 and ends at n. Again, we make sure that all the brackets and braces are paired up. Observe that all of these command lines are within a single input bracket. This means that if the cursor is anywhere inside this input bracket, if we evaluate now by pressing Shift-Enter, all of these command lines, all 5 of them, will be evaluated and Mathematica will recognize all of our definitions. All the values of our preliminary definitions are shown on screen as outputs. While it is reassuring to see the outputs are what are to be expected, they do occupy space on screen. We can suppress the display of these values without losing the definitions by typing a semicolon at the end of each command line. We re-evaluate these command lines by pressing Shift-Enter, and we no longer have the outputs on screen. The next thing that we'll write up is the system of equations for the a sub i's. We don't have to, but we'll create a different input bracket for the system of equations. We call this system or set of equations simply as equations. Since equations is a set of equations, we use the command table to generate the system of equations. The left side of each equation is an integral, and so we use the command integrate. We are integrating the product of the difference between f of x and p of x, and x to the ith power. For the interval of integration, x goes from x min to x max. This is supposed to be an equation, and we use two equal signs for equations in Mathematica. Each integral is supposed to be 0, and so we type equals equals 0. The command table requires starting and ending values for I. I goes from 0 to n. We evaluate this command, and we have all 11 equations displayed on screen. To tidy things up again, we put a semicolon at the end of this command line and re-evaluate. Before we can solve these equations, we need to define what it is precisely we are solving for. The unknowns are the a sub i's, and they form a set of variables so that we use the table command a second time. We'll name the set of unknowns simply as unknowns. Inside the table command, we have a sub I, and I goes from 0 to n. We press Shift Enter to evaluate, and we have our list of unknowns. We tidy things up again, and we use our good friend the semicolon, and we evaluate. Now we can solve for the a sub i's. We use the command solve. We are solving the system of equations that we called equations. And we are solving for the unknowns. We press Shift Enter to evaluate, and we have the values of the a sub i's displayed on screen. We need to have Mathematica plug these coefficients into p of x. P of x, as it is, does not have these values in its Mathematica formulation. There are at least a couple of ways of extracting the a sub I values from the solve output. We will do it this way. We first get rid of the inner curly brackets in the solve output. We should only have the outermost curly brackets. To get rid of the inner curly brackets, we type 2 slashes and the command flatten. We will also give the output a variable name. We assign the output to the variable s. We evaluate this command and observe the output now just has the outermost curly brackets. We tidy up the screen by using the semicolon again. To see the actual p of x with the a sub i's plugged in, we define a new function g of x. G of x is p of x, but p of x as is does not have the a sub i's plugged in. And so to plug in the a sub I values from the output of solve, we type /s. We press Shift Enter to evaluate, and we have the least squares polynomial of degree at most 10. We will compare the plots of f and the least squares polynomial. But first we hide the least squares polynomial. For the plot command, we are plotting f of x and p of x, but with the a sub i's plugged in. And for that, we use g of x. For the plot, x goes from x min to x max. We evaluate this plot command, and we have the graph of the two functions. The graph of f, of course, is the blue polygonal curve, while the graph of the least squares polynomial is the burnt orange curve. With the code all written up, we can easily change the degree of the polynomial approximation. Just for the sake of comparison, we increase the degree of the least squares approximation from 10 to 20. And all we have to do now is re-evaluate each input bracket grouping in sequence from the very beginning all the way to the very end. We can also view the least squares polynomial of degree 20 by typing g of x and evaluating.